Greetings. What is a hydrometallurgist? We're going to find out today because Thandie Moyo is going to speak to us on the things that she does with metals. She is our resident hydrometallurgist, and she'll be telling us all about ore to metal. It's not an easy process. She earned her Ph.D. in chemical engineering at the University of Cape Town, and that's where she learned all about hydrometallurgy, doing work with chalcopyrite, for example, and she'll be telling us a little bit about that today as well. Before coming to Penn State, she served as an assistant research professor at the University of Cape Town and has done a lot of work with hydrometallurgical flowsheet design and conducting fundamental research on sulfide mineral leaching. Thandie, take it away.
Hi, everybody. Thank you for being here. I think I will be putting my storytelling skills to the test today. I still consider myself new at Penn State and will thus be showing less of actual data from my work, but telling you a story of where I'm going with that. And I have decided to anchor that on what I call the copper story. Then I look at sulfide ore processing flow sheets, coal waste, and I close off with recycling. So the copper story. I think we're all familiar with the metal. It's the shiny gold-looking metal, red, also orange, whichever color scheme you think of. And it's been dubbed the metal of electrification because largely of its excellent electrical and thermal conductivity. And this metal's demand is projected to increase threefold by 2050. And what you see on the screen there is just I'm just showing where demand is largely going to come from. It's grid expansion, it's EV and chargers, and all things really to do with the green energy transition. And that said, where do we get copper from? It occurs in a wide variety of mineralizations. It's largely divided into three categories: the primary, the altered, sometimes this called the secondary, and less frequently now the native form of copper. And despite those three categories, the most abundant resources of copper now are the sulfide ores. And even with that genesis, there's different groupings of those, and I'll get into that in my next slide. So just under 15 or so percent of the current known deposit are oxide ores, and notably in the US, about 33% of our copper supply in 2023, according to the USGS mineral commodity reports, 33% came from recycling. What you see on the screen there are just the typical flow sheet for copper extraction. If it's an oxide ore, it usually goes through hydrometallurgy extraction. You pretty much concentrate it and you dissolve it. Less and less with oxides, you grind, you mill, you take it straight to hydrometallurgy and extract. If it's a sulfide, because of the high energy input involved, it's milled, it's ground, it's milled, it's concentrated, goes into pyrometallurgical processing, which can sometimes co-occur with scrap metals which can scrap copper, which can be thrown into the furnace with the sulfide ores. You get a copper cathode, and you get to your finished product. So one of the questions that come to mind as we look at those flow sheets are, what are the alternative pathways that are responsive to the changing nature of our ores in terms of opportunities for co-processing, as well as we see a growth and increase in amount of copper that's coming in at the end of life or end of use. So in terms of the mineralogy, the copper minerals that we exploit, I mentioned the sulfides, but out of those sulfides, there is the chalcopyrite, which is the most dominant one. Notably, it looks like it's got the lowest percentage of copper, but it's also the most prevalent, making about, I think it's over 70% of known copper deposits are coming from sulfide. And that said, it tends to co-occur with pyrite, so that 34.5% isn't necessarily what you get when you extract. It can become as dilute as less than or just above 12%. And in the US, we have Arizona being our home in terms of extracting copper, but we have other significant deposits. I think the oxide deposits actually are not even showing on the map there because of, or on that pie chart, because of how little they are. But those are essentially the leading states in terms of copper production. And it doesn't necessarily always occur on its own. So it's copper production, but it can be co-produced, for instance, with other sulfide hosted minerals like the molybdenites, the nickel, like in laterite ores. So just sticking with that story on copper, why the fascination around copper, at least on my part, is as we talk about increasing demand, we also are looking at a world where our ore grades are declining significantly. You can see from the graph on screen between 1900 to where we are now, how low those grades have declined. The average copper ore globally, when you look at it, is estimated at around 0.6%. It's even lower for the US when you average out. And I think it's around zero point 0.4, if not lower now. How we then process those minerals also from an energy intensity perspective is impacted by this grade of the mineral, noting that the grade, in as much as it refers just to the amount of copper present, there are also challenges around how it's actually occurring, where it's hosted, which minerals host it, and how it's associated with other minerals, which is what I will get into as I move on with this presentation. So key challenges from our traditional processing flow sheets is how, as I mentioned, the minerals coexist, or how they are distributed within the ore, which mineral is more abundant, what is the grain size distribution of that mineral, what is it associated with, the liberation characteristics of the mineral. All that is quite relevant, especially when you're looking at the earlier stages of the flow sheet in mineral processing, because it very much speaks to how much energy is put into the process to liberate the mineral. So in many instances, when we talk about mineral liberation, we talk about the energy input in sulfide mineral processing. We tend to focus more on the pyro side of things, but in the mineral processing stages itself, there is quite significant energy input into extraction. I put those micrographs there just to show you. On the one, that's our interesting low-grade copper ore from somewhere in the US. What you see is a lot of different mineral grains there, and different, actually, like, I'm calling it mineral grains isn't the right term in terms of actual, it's pulverized minerals, but the magnification is not big enough for you to see the copper grains in it. But what I wanted to contrast it with is what you then see to your right, which is the actual copper bearing minerals within that sample, just the significance of how little when we talk about how much, when we talk about mineral grades for sulfide minerals. So now looking at the typical flow sheet for this, as I mentioned before, sorry, I'm looking for a laser pointer. I can't find one. So looking at that process flow sheet there for copper, the conventional route, the one that in solid lines will be you get your mineral in, it goes through comminution and flotation, and I pull out the flotation aspects of the circuit there, because the comminution aspects, because I'm trying to highlight the different unit operations that are there and the different stages that are involved. Essentially, what we're doing here, we're trying to move from an ore that's, as I said, maybe just under 1%, and you want to put to get to a concentrate which can be anything between 20 and 30%. In some instances, depending on their processes, it can even be better, but that's a function of mineral liberation, the surface chemistry as you float the mineral. When I was talking about mineral associations and things like the locking of the minerals, those are the things that are put to the test here. If your mineral is locked, you essentially cannot float it. You need to grind it even finer to be able to liberate it from its associated minerals. And as I spoke about the complexity of mineralogy, if you're extracting a mixed ore, sulfide and oxide ore, once you get into that, you risk losing a lot of your copper if your flow sheet is not designed to respond to that, because you might float the sulfide but have your oxide reporting to tailings. Otherwise, as you go further down the flow sheet, once you have gotten your concentrate, the processes tend to remain pretty much similar, except when you're now looking at changing the process chemistry. Traditionally, if you're going the hydrometallurgy route, it's largely been sulfuric acid leaching in the presence of ferric and ferrous, but we see more and more of some dilute forms of hydrochloric acid taking advantage of that copper 1, copper 2 redox couple in terms of extracting the mineral. And this is where I'll also zoom out on the process, which is in a blue box there, the actual leaching stage, because that's where quite a bit of the fundamental research taking place in my lab is. I highlight there just some of the mineral composition and type properties that impact decision making in the flow sheet when you're looking at the unit operations to do with the mineral processing stages. So mineral processing would be referring to the comminution aspect, the crushing and the grinding, and that also comes with some screening and classification, so we would call it, to ultimately get to the targeted particle size that you desire. And that particle size, the decision around particle size, you will find in literature, it's stipulated in a range. You're given like maybe minus 75 to 150 micron particle size distribution. But in reality, that particle size distribution is something that's responsive and should be adapting to the mineral characteristics of your ore, because if you have fine-grained minerals, or if you have interlocking in your minerals, as I mentioned, or just poor liberation properties, you might find yourself requiring to input more energy into your process to mill as fine as maybe minus 35 microns. There are processing plants that are known to do that, and that comes at a disadvantage as well, because now you have a trade-off between how fine do I mill to liberate this mineral, and how much of it you will lose in flotation, because in the flotation circuit, essentially, you are taking advantage of the hydrophobicity of your minerals and relying on bubbles to carry it up to float while the gangue minerals sink. So the separation factors get to be compromised. So a lot around the thinking of how to exploit what you have learned about your mineral characteristics to how you get your flow sheet to be agile enough to respond to this, especially in the world of heterogeneous minerals, heterogeneous ores. So here I just list some of the parameters that are established to be relevant. What I spoke to before were parameters that are relevant more to mineral processing side of things. But here now I'm talking to parameters that are important to actual extraction. Once you have concentrated your mineral, if you're concentrating, or once you have milled and are sending it through to your leach circuit, what is it that matters when it comes to extraction? Of course, particle size. We talk about particle size because it increases the surface area, but particle size beyond the ability to liberate the mineral to float it, particle size also speaks to how, as I said, how liberated your mineral is in as far as contact with your lixiviant once you start leaching. You want to know your pore structure and porosity. This is important when you're making decisions, especially when we're dealing with the lean ores that we're working with now. Sometimes you do not want to expand that much energy grinding to a fine particle size because the cost economics are not favorable. But if you have a good pore structure and good porosity of your mineral, you're looking at technologies such as heap leaching, that becomes relevant in terms of understanding the flow of your lixiviant and ion migration within your dissolving mineral. We look at other aspects like crystallinity, amorphization, all those aspects to do with texture that we take advantage of when we're looking at selecting our extraction process routes. Um, so I'm giving here an insight more into what we then do in my lab. This is not from any of the work that we do, but just an insight to what it is that I mean when I'm saying we require mineralogical characteristics in as much detail as we can to be able to define a flow sheet and predict how our minerals will behave once we put them in the process. And sometimes this pre-simulation of the processes helps us understand how responsive our flow sheet is to our changing mineralogy. So in this case, you come in with all those parameters, you define what is in your feed stream from a mineralogy perspective in terms of mineral composition, in terms of particle size distribution. There is opportunity to keep going even finer and finer, bringing in textural and morphological features into this design. And through that approach, you are able to, by defining your input streams, which you see as ore feed going into the ball mill, and defining your process parameters, you ultimately are able to predict what comes out as your tails or your concentrate from each of the unit operations within your process. So that is where the direction that some of the work that's going on in my lab is going. But I'll highlight where the challenges are, which are what brings us back to focus more on fundamental aspects of the research, because at that point, in terms of process flow sheet, it's applied. We're applying mineralogy, we're applying our understanding of the chemistry, and we're simulating those processes. But we cannot do that without the data and parameters to that. So in the case of chalcopyrite, it's a mineral we have been leaching for quite a while. There are some established chemistries, but those are anchored on mineral acids or other established chemistries like ammonia in the presence of some oxidant. Typically, if you're working with a more concentrated mineral, it will be pressure leaching. But if it's the leaner ores, which are heap leached, we take advantage of the iron 2, iron 3 redox couple in heap systems, and sometimes a microbial leaching. And more we see the exploration of surfactants to aid in terms of wettability of the ore, and even in terms of how our gas bubbles interact in our system when introduced. And what we're trying to do in my lab is to deviate a bit from those inorganic acids, mineral acid systems to working with organic acids. The reason for that being really, if we're going to be working with leaner ores and we are looking at, I think you'll be familiar with what happens in the dewatering of our tails once we're done. It's a significant issue, and you have residual acid left in solutions. And there's aspects to do just with, I'll pull up a slide in the end to kind of like say, hey, this is what our organic acids, how our organic acids are more friendly than our mineral acids. So this slide just summarizes some of the advantages of that, but highlights the gaps that are existing there that we have established. There is literature that speaks to that. This works, but it also highly relies on hydrogen peroxide as the oxidant. which is something that we know from mineral acid leaching that it's not widely used industrially, partly from a cost factor, partly from a safety issue. And we are exploring to understand how this works when you're working with organic acids, but also to see if we could take advantage of the traditional uh, uh, cuprous or ferric ferrous redox couples in our systems. So this would be what we do. We take our minerals, we make them into electrodes in terms of this primary sulfide. In that case, that's chalcopyrite, and we really look fundamentally what is happening on the mineral surface, and this is through both analyzing the current responses of this semiconductor material, and also looking at the solutions that come from there to track what elements come into solution, and also looking at the surface of that electrode once it comes out to then draw a full picture around that. We collaborate with other research groups that do some molecular modeling to try and understand and predict what the surface reactions would be, or to explain the phenomena that we see. And just a tease into the kind of results that we have. What you see to the far left of your screen are more really trying to understand our chemistry. As I said, this is organic acid, and you're adding hydrogen peroxide to it as an oxidant. You're looking at the current response with regards to that. And as expected, you can see that there is very poor reactivity when you're using oxygen, just shown by the very low currents there. And this significantly is higher for hydrogen peroxide because of it's easily reduced on the mineral surface. But in this case, we were studying the solution, and we just wanted to understand this on a non-reactive surface. We look at this as well on the mineral surface, and you can see from the currents there as well which oxidant would be more impactful when you are dissolving the mineral. So in this case, those current densities are analogous to the rate of the reaction, how much of the reaction is taking place. In the last slide, there is current density. So essentially, after we establish that at this potential, this mineral will leach, we fix the potential, and we run it for a period of time, and use the charge to determine just how much we track the charge. So the amount of charge passed in terms of integrating the area under those curves, the higher the charge passed, the higher the extraction of the mineral. And we can correlate this with the actual target element in solution, and work back using some electrochemistry equations to determine how many electrons were transferred, and hence come up with the mechanism of oxidation of our mineral. What we do with this, before I move on here, once we have that information, we can now go back to the simulations that I spoke about earlier, because we now have more insights into these parameters, and we put it in there. We're able to more effectively simulate what's happening in the process, and determine things like the exit stream, and also determine what would be the composition of our leachate. Here, it's another aspect of the work that we're doing that's now looking at coal refuse. We've seen quite a growth in interest in coal refuse as a source of critical minerals, including rare earth elements. But what we don't really understand at the moment, which is why we try and model this system, is what is it that we know about our feed streams, and what will it help us, how will it help us define the processes that we can use? And because of the heterogeneity of those streams, and where they are located, we're also looking at, does it really make sense to design a flow sheet for a very small volume of waste? So how do we go about using insights from mineralogy to design process flow sheets that will be agile enough and adaptive to be able to be employable across different feed types coming from that coal waste? So what we've done here, we started working on the underclays, which is still quite new as well, trying to figure out what hosts our minerals and our target minerals. Yet at the same time, we're also trying to figure out what processes we can adapt to be able to extract these minerals in an environmentally sustainable manner. So here is just what the earlier phases of what we've done in process in mineral characterization, looking at our mineral associations, looking at our distribution of the minerals thought to host the target elements. We look at this prior to extracting, and we then look at it post extracting to see how our chosen process routes have changed the structure of the feed of the solid materials, and to also estimate the pro predict the stability of those residue materials. So in this particular case, the underclay we've just characterized is one that contains about 853 ppm of lithium, but we also note that it's got significantly high concentrations of aluminium and iron. And where this comes into play is, I'll come back to this slide, is just looking at what then happens based on our choice of reagent in terms of core extraction and selectivity. So just going back to here, I was just speaking to I just want to speak to the traditional route for processing this type of materials, which will involve calcination, essentially just to try and break down the structure and make your target metal accessible, and how we then exploit what the technologies we're trying to do is, in this case, we're looking at, rather than going the calcination route, we want to see if we can use more physical, thermal approach to activating this mineral. And in this case, we were using mechanical activation to do that. And if you're looking at the diffractogram on screen, you will see that the blue curve shows you the mechanically activated and shows you the peaks of the clay minerals to essentially have disappeared with this amorphization stage, which then means you have altered the crystallinity of that material, and we then leach it with the organic acids again. And in this case, we essentially were doing a screening test here to see which acids would more effectively extract those minerals. We started by trying out water, and our recoveries were pretty low, suggesting that in as much as we had amorphized the sample, there is still some structural integration between the target element and the mineral phases that we have. And when we then introduce the different organic acids, we then get to see that extraction pretty much increase instantly to a point where kinetics are not an issue. Within the first 5 minutes of the extraction, you already have recovered over 80% of your mineral for some of those organic acids. And we then looked at how selective those were, because we're trying to get to a point where is it possible to take advantage of the choice of reagent to selectively extract target minerals over the associated minerals. What we haven't done yet is to actually, to look at the residues from this extraction to see what has changed in their structure. And we haven't yet gone back into our simulators to simulate this and be able to predict what would happen in the long term with those solid residues once they're disposed of into the environment, or to at least explore what opportunities are there in terms of how else they can be used. The one thing that motivates partly the use of organic lixiviants is the fact that once we wash our residues, we want to be able to propose alternative uses for those residues, at least with some extent of confidence that whatever residual lixiviants in it are biodegradable and would not be causing further harm as they are in further applications. So here, this is a question I would typically get: who said organic acids are greener? So this slide, you don't have to read through it, but in case it was a question you had in mind, why organic acids, this just kind of gives you some thoughts into where we come from in going that route. And this the last slide, the last portion of this presentation, it's got nothing to do with our actual natural minerals. It's more to rethink how we deal with our waste streams. And in this particular research, we're looking at the recycling of cathode materials and how to keep it in the technosphere and how we are approaching this. So this is just the rationale that we have for that, that looks at, this is a study done for the US where we're looking at certain percentages of some of those critical materials coming from recyclables. I think the motivation for this is pretty clear and doesn't need to be drummed in. But how we come in to look at this is somewhat similar to the approach we take with our primary minerals, where we first want to understand what's in it. We want to understand how this actually failed in the first place. From that perspective, we want to work forward to regenerating the material. So in our case, we're not looking at producing lithium salt or any of the input raw materials. We are trying to work with what we have essentially to recycle, regenerate, or upcycle it even. So we take our cathode materials and in a pressure reactor, we essentially relithiate and get a new crystalline material, and we are targeting dual structured in terms of the materials that we started off with, and because that's been shown to offer more stability and more recyclability once it's done. And I'm just highlighting here the fact that the tools that we're using are pretty much similar and what we have achieved thus far. So you can see the spent cathode material, lithium manganese oxide, and what we then regenerate and how we then introduce impurities. We know those materials will not be pure, but we are intentionally going through doping the materials in effort to have a more stable material, one that cycles more, and possibly one that outperforms the initial feed material in our process. And this is just some of the effort we've been making towards characterizing those materials post-production to see how they're working. And we're taking advantage of some of Penn State's new toys to show whether or not we're successfully achieving what we're doing. So this is just some XPS data that actually shows how far we are in terms of getting the different manganese 3 to manganese 4 ratios in our cathode material, because that is something that's important to how this material will perform. And just some an SEM AM micrograph illustrating that there. And as my final slide, I just thought that this is something that's interesting in terms of the trends around studying extraction of the processing of minerals in relation to mineralogical insights, how that trend has shifted over time, and noting where most publications in that space come from. So I personally think the flattening of walls between the mineralogical sciences and the process flowsheet designers and extraction processes is an area of growth. With that said, I want to acknowledge my 3 PhD students that worked tirelessly to get me standing here and talking. And I've lumped everybody there into the mineral characterization lab, but I think I will mention Maureen and Nick, who have been playing around with the SEMAM at Penn State. That's helped us get some interesting pictures and thinking about how to work with it to assist us in this approach as we venture into this flowsheet design informed by the mineralogical characteristics, and of course, thanking those that contribute financially. Thank you.
Great, thank you, Thandie. We have time for questions. We're going to use our microphone here in the catch box. Does anybody have any questions in the room? Anybody? Yeah, Maureen.
Thank you. So, Thandie, how close are we to being able to have, or like, what are the major steps to being able to have widespread recycling and reuse of copper, lithium, these battery elements? Like, where are we now in terms of what we can do compared to where we want to be, and what are kind of the major steps that we need to figure out along the way?
Thanks, Maureen. Are you asking specific to batteries on, or
Like,
just end of
speak
life?
specifically to let's keep it
Yeah.
simple. Let's say
Yeah.
batteries.
So I think specific to batteries, I actually think from the processing side of things, we're pretty far advanced. I think our biggest challenges are in separating the materials, and I think there is a world where taking advantage of robots, yeah, in doing that might accelerate how well we can do that, because I think we have somewhat established the material. Once you've isolated it, is fairly recyclable, or something can be done with it.
Are there programs? I can't remember if it was in one of these talks or not, but in the past year or two, someone kind of blew my mind by pointing out that that e-cigarettes have like lithium batteries in them and are not recycled, and so every e-cigarette that gets used gets thrown away, and that's like lithium getting taken out of the system. Are there, I don't know, is that a significant loss? Are there like, are there things like that, like streams that we're not capturing?
I think there are streams that we're not capturing, and a lot of that would be resting on policy, unfortunately, and maybe also just general infrastructure to achieving this, because it not just from the e-cigarettes. A lot of batteries are actually, there's a big focus on the big ones from, EVs and all that, but there's many other batteries that we use, whether it's the battery in your phone, your laptop. There's a lot of leakage that's there, and I think it's largely a policy issue and maybe a social issue, like how do we work all together towards, I would say, unlocking that stream.
All right, any more questions?
Penn State has a sewage treatment plant, and it has copper problems with its sludge. And so you have to take the sewage sludge into a landfill, which is a secure landfill, which is expensive to dump the waste and transport it there. If one could take the copper out, then the biosolids could be used in a beneficial way, on farmland and for crop production and so on. So here, maybe the copper is not that valuable in terms of the amount, but if one could get the copper out, and then you would save the money on the disposal of the organics, maybe there's a profit there to the university. So can one do a research analysis of that, where the cost on the one hand, the benefits on the other, and then you'll get some copper anyhow, whether you wanted it or not. And again, I'm not sure how much copper you could collect that way, but that's a very practical consideration for the university, as an example.
Thank you. I wasn't even aware of that waste stream as a potential source for copper. That's quite interesting. I think I can't answer to what could be done, but I have more questions around. So where is this copper sitting? Is it like in a residue, or is it in a solution already? Because all that has different implications to what that would look like. But it certainly sounds like an interesting exploratory project for somebody. Maybe the next time I have an undergrad that's willing to work with sewage, they could explore that to just figure out where it is, and the cost benefits to that as well. There's
Yeah,
somebody
Brett
with it.
Spurberg, if you have a question, feel free to unmute.
Yeah, thank you. Thanks for an interesting presentation. I'm listening in via Zoom here. You mentioned bioleaching briefly. What do you see as the future of bioleaching? Are people engineering bugs to enhance mineral extraction that you're aware of? Do you see a future there?
Yes, yes, thank you for that. Yes, in fact, I'm working with somebody at Missouri, and we are trying to bioengineer bugs, hopefully to in situ leach, if that will get to that, if we ever get to that point, really looking at it from a perspective of lean ores in particular, because that's where the minerals that host copper remain the same, difficult to leach, but we still need to be able to extract them to address the demand for the metal. So I think there is a future in bioprocessing. There is an established bioprocessing. I think BHP has one already, but that's more an on the plant one, and it's not necessarily. I think it's what's it called? It's their process, so it's not available to us. But I think there is future in bioengineering to improve our extraction.
Okay, thank you.
Okay, I guess I have the catch box, so I'll go next. Early in the talk, you were making the point that it's very important to characterize the microstructures of these materials in order to figure out the best way to process. And those abilities have been around a long time. I've never really had the sense that there are mining companies out there willing to pay people to do that kind of close characterization that you're describing, because it takes a lot of time and money basically to do the kind of work that you're describing. So how does it happen, I guess, in the ideal world, that these resources are characterized and the way that you think they need to be in order for you to set up your flow chart and determine the optimal way of processing these materials?
Thank you. I think we're seeing more and more of that happening now because of, I suppose, the one aspect is from an environmental perspective. Mining companies are facing more significant liability to what they discard of. So if we're not going to characterize for process efficiency, they are characterizing to at least be saying we are not doing you more harm than good. But on the other side, there is a lot more reports on flowsheet optimization that's been done based on that characterization that has really saved companies significant amounts of money. Just coming to mind, numerous copper mines like that have had to alter their flowsheets. Like I initially said, it was a plant issue that they would float their mineral and extract the sulfide, but would lose a significant fraction of their oxide to tailings. So by understanding their mineral makeup, they made a choice, which was, we're going to alter our flow sheet. We're going to take our mineral, leach it first so we get all the oxide out. Then once we've leached it, take it back to flotation. So we float the sulfide out. So I think it's a cost benefit aspect. Once the mining company recognizes what they are losing, they revert back to more mineral process informed decisions around their flow sheet. We see that as well with gold, as well in the gold industry. It's largely with the sulfide ores, I would admit, where we see that happen a lot.
So do you think the mining industry will be hiring trained mineralogists in the future to do this work? Is that a field that you see is going to be opening up? Or do you think that mining companies will be turning to academia and finding people in academics who are willing to do it?
I think bigger mining companies are already doing that. They already have acquired some of those instruments, and at least in some of the institutions that I know, some of the instrumentation to be, it's actually there because it was sponsored by mining companies that needed the research done. But also, I do think there's opportunity for academia to collaborate on this, because not everybody has the time and the means to buy this, because ultimately at the end it's a recommendation towards the flow sheet that they then carry forward. So it would more like be a consultancy. So if they can consult on academia for that, it's not always something they keep resident, at least at this stage.
Thanks.
All right, any more questions? Either on Zoom or in the room? Okay. We'll be ending a little early today, but that's not a problem. We can thank Thandie one more time for her presentation. And I know last seminar I said we have one almost every Monday until the end of the semester, except for holidays, but we actually have a postdoc and faculty meeting next Monday. So we did a bye-week for Earth Talks, and then the following week is also a bye-week, and then we'll have a semester except for breaks, holiday breaks. But yep. And this recording will be posted to our YouTube, our easy YouTube. So thanks everyone.